Manhattan's street grid ignored almost everything actually on the ground when engineers drew it in 1811, the hills, the streams, the natural shoreline. None of it mattered once the lines went down on paper. That single decision still dictates how every taxi, water main, and subway line moves through this city more than 2 centuries later, long after anyone remembers whose signature actually approved it. There's a 41-mile pipe that still moves water into Manhattan using nothing but gravity. There's a bridge that killed and disabled the men who built its foundations underwater, using a technology nobody had tried at that scale before. And there's a concrete wall from the 1960s that held back an entire river on September 11, 2001, when almost everything built on top of it collapsed. I dug through engineering reports, infrastructure archives, and construction records spanning 4 centuries, and used advanced AI to trace how this city actually got built, decision by decision, piece by piece. Forget the wars and the mayors for a minute. This is the story of the engineering decisions that actually built New York. Dutch traders settled this island in 1624, and the British took it over in 1664, but neither one left much of a physical mark beyond a few streets and a defensive wall that gave Wall Street its name. Why would engineers deliberately erase the natural landscape instead of building around it? The decision that actually shaped the city came in 1811, when state-appointed commissioners approved a plan to lay a rigid grid of numbered streets and avenues across nearly the entire island, most of which hadn't been developed yet. Surveyors walked the entire island with chains and compasses, driving iron bolts and stone monuments into the ground at every intersection to mark exactly where each future street would eventually run, years or decades before construction crews ever showed up to build them. The plan ignored the island's actual terrain almost completely. Surveyors flattened hills, filled in streams and ponds, and cut through solid rock wherever a straight street line demanded it, reshaping the physical land to match a plan drawn on paper rather than adjusting the plan to match the land. One steep rocky stretch, later cleared for what's now Central Park, got skipped over entirely at the time. Engineers judged the terrain there too difficult and too far uptown to bother grading for streets that wouldn't see buildings for decades. I love that the exact land engineers found too difficult to flatten in 1811 is the same land that became Central Park's rugged interior 40 years later. That single surveying decision still shapes how every street, subway line, and water main runs through Manhattan today, a rigid pattern laid down before most of the island had a single building on it. Just as the grid was going in, New York State began digging a canal 363 miles long, connecting the Hudson River to Lake Erie, a project critics mocked at the time as Clinton's ditch after the governor who pushed it through. Engineers with no formal training in canal building designed and built the entire route by hand, using teams of oxen, hand tools, and a self-taught approach to lock design that let boats climb roughly 565 feet in elevation over the length of the route. The route required 83 separate locks to manage the elevation change in stages, along with aqueducts that carried the canal itself over rivers and valleys using stone arches, engineering problems nobody in the country had solved at this scale before. The canal opened in 1825, and its effect on New York City was almost immediate. Goods that once took weeks to move from the Great Lakes to the Atlantic could now reach New York Harbor in days, funneled entirely through the port at the bottom of Manhattan. Freight rates dropped by more than 90% on some routes within a few years. New York's harbor hadn't gotten any bigger. What changed was the sheer volume of cargo one engineered waterway could now dump into it, and that volume is what turned the city into the country's dominant port for the rest of the century. Quick pause. If this is the kind of history you want more of, subscribe so you don't miss the next one. And if you're finding this interesting, a like goes a long way. By the 1830s, wells and cisterns couldn't keep up with the city's growth, and fires kept spreading because there wasn't enough water pressure to fight them. Engineer John B. Jervis, fresh off the Erie Canal project, designed a solution that moved water entirely through gravity. A masonry aqueduct 41 miles long, running from a new dam on the Croton River down to reservoirs in Manhattan, dropping just 13 inches of elevation for every mile of distance. Crews built the aqueduct as an enclosed, egg-shaped brick and stone tunnel, roughly 8 feet tall, carrying the flow across valleys on stone bridges and through hills via cut tunnels. When water first moved through the system in June 1842, it took 22 hours to travel the full 41 miles into Manhattan, arriving without a single pump. A masonry dam 6 miles upstream created a reservoir capable of holding 500 million gallons, feeding the aqueduct at a steady, deliberately engineered rate, no matter how dry the season got. Where the route crossed the Harlem River, engineers built High Bridge, a stone structure resembling a Roman aqueduct, to carry the water across on 15 masonry arches rather than route it underground. I still can't quite believe an aqueduct with 0 pumps moved water 41 miles into Manhattan using nothing but elevation and basic math. The completed system could move 90 million gallons a day into a city that had never had reliable water pressure before. Fire risk dropped immediately, and for the first time, New York's growth wasn't capped by how much water its own island could hold. A second, larger aqueduct followed decades later, and by the 20th century, the city had extended the same gravity-fed principle across 2 entire underground tunnels, stretching more than 100 miles into the Catskill Mountains. By 1853, the city set aside land in the middle of Manhattan, most of it swampy, rocky, and considered unusable, to build a park nobody had designed yet. Frederick Law, Olmsted, and Calvert Vaux won the design competition in 1858, but building their plan meant moving the land itself first. Crews used gunpowder to blast through Manhattan schist, wherever bedrock sat too close to the surface, moved more soil and rock by hand and cart than most infrastructure projects of that era, and engineered an entirely artificial drainage system underneath the park to keep it from reverting back to swamp. Workers relocated entire sections of soil from one part of the park to another, built an artificial lake with an engineered clay lining to hold water without draining into the bedrock below, and buried more than 60 miles of drainage pipe under what looks like natural ground. Every lake, pond, and rolling hill inside the park is artificial, built on a drainage network of buried pipes that still channels rainwater exactly the way engineers routed it more than 150 years ago. It took over 15 years and thousands of workers across different phases to finish grading, planting, and plumbing what looks, by design, like it was never touched by machines at all. Connecting Manhattan to Brooklyn, then the 3rd largest city in the country on its own, meant spanning nearly 1,600 feet of open water deep enough that no one had ever tried a suspension bridge at this scale before. Engineer John Roebling designed massive underwater foundations built using pneumatic caissons, sealed wooden chambers pressurized with compressed air, lowered to the riverbed so workers could dig the footings out by hand, while the surrounding water stayed out. The compressed air came with a cost nobody understood yet. Workers surfacing too quickly from the pressurized chambers developed a condition doctors called caisson disease, now known as decompression sickness, or the bends. At least a dozen workers died from it during construction, and Roebling's own son and successor, Washington Roebling, was left partially paralyzed after spending too long in the caissons himself. It gets me every time that the tallest structure in New York in 1883 was finished only because of work nobody could see, sealed underwater inside pressurized wooden boxes. Above water, crews spun the bridge's 4 main cables from more than 14,000 miles of steel wire, a cable spinning technique adapted directly from Roebling's own wire rope factory. When the bridge opened in 1883, it was the longest suspension bridge on Earth, built on foundations nobody had fully understood the cost of at the time. Each tower rose from its underwater foundation using massive blocks of limestone and granite, load-bearing masonry piers strong enough to anchor cables under tension nobody had calculated for a span this long before. By 1900, above-ground elevated trains and horse-drawn streetcars couldn't move people fast enough through a city already packing more than 3 million residents into a few square miles. How do you dig a tunnel under streets that can't ever actually close? Chief Engineer William Barclay Parsons chose a construction method called cut and cover for most of the route. Crews opened a trench the width of the street itself, built a concrete and steel tunnel inside it, then covered the whole thing back over so traffic could resume on top. Where Manhattan's bedrock sat too close to the surface for a simple trench, crews blasted through solid schist with dynamite instead, working block by block underneath streets that stayed open to traffic the entire time. At peak construction, roughly 7,700 laborers dug the tunnels almost entirely by hand, using picks, shovels, and hand drills, since heavy earth-moving machinery barely existed yet. Ventilation grates, drainage systems, and electrical conduits all had to be engineered into the tunnel design from the start, since retrofitting them after the tracks went in would have meant tearing the whole thing open again. The subway opened on October 27, 1904, running from City Hall to 145th Street in about 26 minutes. Cut-and-cover construction remained the standard method for building subways under city streets for most of the next century. By the time later lines pushed further into Brooklyn and Queens, engineers had switched to deep tunneling and tunnel shields for sections where cutting open the street simply wasn't practical anymore. For most of the 19th century, a building's height was limited by how much stone its own walls could support at the base. Since masonry construction required thicker walls, the taller a building got. That limit disappeared once builders started using internal steel skeletons instead, frames that carried a building's weight through a cage of steel columns and beams, rather than through the exterior walls themselves. Exterior walls became a lightweight covering rather than load-bearing structure, freeing architects to build taller with less material at the base. Elevator safety mattered just as much as the steel. A safety brake, patented decades earlier, made it possible to trust an elevator car at height. Without either innovation, none of the buildings that followed made practical sense. Elisha Otis had demonstrated a working safety brake back in 1854, a mechanism that locked an elevator car in place automatically if its lifting cable ever snapped. The Woolworth Building used this steel frame method to reach 792 feet in 1913. The Chrysler Building and 40 Wall Street raced each other through 1929 and 1930 using the same basic technique, and the Empire State Building topped them all in 1931, rising 1,454 feet using more than 60,000 tons of steel assembled in just 410 days. Robert Moses never held elected office, but he controlled more construction authority than almost anyone in the city's history, running a series of appointed agencies that let him design and build public works with almost no outside oversight. Moses's projects added hundreds of miles of parkways, dozens of bridges, and thousands of acres of parkland across every borough over 4 decades. His bridge and overpass designs deliberately used low clearances on several parkways, engineered specifically to keep buses and the riders who depended on them off certain roads leading to beaches and parks. The Triborough Bridge, opened in 1936, needed 3 separate spans engineered to connect Manhattan, Queens, and the Bronx at a single junction, a design problem unlike any single bridge crossing before it. Moses later oversaw the Verrazano Narrows Bridge as well, which held the record for the world's longest suspension span when it opened in 1964, a title the Brooklyn Bridge itself had once claimed 80 years earlier. Later highway projects, including the Cross Bronx Expressway, required cutting directly through dense existing neighborhoods, engineering a route that prioritized traffic flow over the streets and buildings already standing in its path. Building it required demolishing thousands of buildings block by block, a scale of urban demolition that made the highway one of the most disruptive engineering projects the city had ever authorized in a single stretch. Building the World Trade Center in the late 1960s meant excavating 6 stories down through land that sat partly on the Hudson River itself, ground that would flood immediately once crews dug below the water table. Engineers solved it with a technique borrowed from Italy and never before attempted at this scale. A slurry wall, built by digging a 3-foot-wide trench down to bedrock, filling it with a heavy clay-based fluid to hold the trench open, then pouring concrete into the trench before removing the fluid. The finished wall ran 3,500 feet around the site's perimeter, forming a watertight basin engineers nicknamed the bathtub, holding back the Hudson River while crews excavated the site itself. Crews poured the concrete underwater using a method called tremie, feeding it down through a pipe to the bottom of the trench so it displaced the slurry fluid without mixing into it. Excavated material from the site got barged across the street and dumped into the Hudson River itself, creating the landfill that Battery Park City now sits on. On September 11, 2001, the towers collapsed directly onto that same basement. The slurry wall held. Engineers who inspected it afterward found it largely intact, and the subway and path tunnels running through the site never flooded, a catastrophe averted almost entirely by a concrete wall poured more than 3 decades earlier. Personally, I think the slurry wall is the best example in this whole story of engineering nobody thinks about until the one day it actually matters. One World Trade Center opened in 2014, built on the same foundation. Hurricane Sandy tested that same wall again in 2012, flooding surrounding streets while the basin itself held. The engineering decision that mattered most on this site turned out to be one nobody could see once construction finished in 1970. None of these engineering decisions got made by the same people or even the same century, but they all solved the same basic problem. How do you keep building on an island that was never actually big enough for what New York became? The grid still routes every street. The Croton system's successors still move water entirely by gravity. The slurry wall still holds back a river most New Yorkers never think about. What all of this actually proves is that New York's shape was never really designed once. It got re-engineered decade after decade by whoever solved the physical problem the city had outgrown yet again.
If you want to see the engineering still holding this city together, walk the old Croton Aqueduct Trail, or look up the slurry wall exposed inside the 9/11 Museum. Subscribe if you want more cities broken down by how they actually got engineered, and tell me in the comments which city's infrastructure I should dig into next.